Hi guys, I've not done any ATX repairs for a few weeks, mainly because I was wanting to modify the analyzer, because this piece of junk, basically as it was, only powers up when there's a 12 volt supply, so it can lead you a right merry dance. You can think you have a completely dead power supply that's actually working apart from the 12 volt rail, so I've modified this now, so this actually powers up if any voltage is present, regardless of whether it's just standby or anything else, so let's have a look at this power supply. Initially we connected this to it while we were just checking all these power supplies, and we said this has no output, but what I'm interested to see now is whether with our modified analyzer, if that's the case, or maybe it has 5 volt standby, I can't remember if we actually checked it with the multimeter previously or not, so let's have a look. So, and we can use a multimeter as well, so there's our analyzer. We can connect this to the power. We'll connect it via the light bulb and let's see what it does. Okay, so there's the analyzer. I've got the voltmeter. I won't attach that just yet. I will check if this says it's dead. I'll check the 5 volt standby, but this should come on. That's the modification. Now I'll link the video where this is modified in case you haven't seen it. It's a very good modification, it seems, for these. So anyway, let's just power this up. I've taken the 100 watt bulb out, so I just have the 60 watt bulb, and I want to see if this draws any power when we switch it on, if it does anything, Okay, so let's switch it on and let's see what it does, so I've got the light bulbs connected in the circuit, both the light bulbs, that's 160 watt in total. Let's apply some power and see if this actually does anything, Well, the bulbs flashed and went off, and it's actually on, but the 5 volt standby is unstable. Let me zoom the camera down. You can see what it's doing, There, so you can see the 5 volt standby is all over the place, and all the other voltages are saying low, which suggests there's probably no output on any of the other voltages, so it's not so dead as it would appear now we've actually got this analyzer modified, I've switched it off, so I'm assuming the 5 volt standby, will eventually go away, so okay, that's our supposedly dead power supply. Isn't quite so dead as it seems, so let's open this up and let's have a look to see if we can see any obvious reason why there's problems with it, okay? Okay, so what have we got? And I can be confident there's these big capacitive discharge because the thing effectively, the standby was running, so it was drawing power. But I can use a voltmeter just to check. There's no PFC in this, well there is. There's a passive PFC, a big coil here, so I can connect my voltmeter directly across the bridge rectifier, and this will show me if the capacitors have any charge in them, if it had PFC this wouldn't work. You can't test it this way, but there's no no active PFC, if it had active PFC this wouldn't work. So you can see we've got that 12 volts in there, remember this will not work if you see 3 of these heat sinks, or if for any other reason you've got active PFC, but okay, so they are basically discharged, about 12 volts in them. Looking down here I can see a lot of very suspect looking capacitors, I mean that's got a dome like St. Paul's Cathedral, on that one, so the first obvious thing is with this is we need to change some of the capacitors. So let's get the PCB out of this and let's have a look to see what we've got. Let's see how bad this is. It's quite clean inside. That's a bit unusual for these old power supplies. but this one's quite clean inside at least. Okay, just take that screw out, and one more down this corner. Move this wires out of the way a little bit. Okay, I have it unplugged from the mains, by the way. You need to stay safe. Don't, if it has an on-off switch, this one doesn't. Don't trust the switch, especially if it's a single pole switch. Yeah. And especially if like you've got mains leads like me that can go in either way round, so there's no live as neutral as such. Yeah. And even if you haven't, can you really trust the people who built this to put the switch in the live and not in the neutral wire? Yeah. Do you trust them really with your live? Really? It appears to me that, yeah, the power comes down here off these brown and blue here, so I think we can get this PCB out by desoldering these two wires. There's no plastic, you know, like the little thing around here that's, it has like a bit of a plasticky thing pushed on it, but normally they have like a ring, a plastic ring thing in there. Obviously it costs a few cents, so this was slightly cheaper. Yeah, that was slightly cheaper, so they used that. Okay, that's out of there. So we need to unsolder these, and I can see we have a voltage selector switch as well. But the easy things, it looks like we can just unscrew that for now to get this. Will it come off here easily? Otherwise I may have to unsolder those wires as well, actually, to get to the PCB. Let me see if I can just find another screwdriver that actually might fit that. Yeah, there we go, I've got one. Let's have a look if we can actually just yeah, we can. So let's just unscrew this. That's the top PCB. In fact, actually I can unscrew both PCBs on this. Will it come out? No, it won't come out easily, that one. I'm trying to unscrew this thing. Yeah, that's not going to help me, but we can take no, that's not going to come easy. Let's do it the other way. Okay, so first of all, let's take off the power wires coming in. Yeah, so let's just get on here. Bit of solder. Bit of solder is going to help here. That one should be, yeah, there we go. Other one. Bit of solder. Come on. Doesn't quite want to give it up. That's I'm trying to be careful not to splash solder everywhere. Yeah. When I take this out of here, just wipe that off. And I can always use a bit of solder braid actually, just to clean the thing there. It doesn't easily want to quite come out of there. I've got it. It's out. So we can now lift our PCB if we're lucky. If we're lucky. There's another cable tied down inside here that's holding the whole thing together. Another wire cutters. Too many things on my desk. Here we go. Let's get a cable tie off here. Yeah, that's off. Now can we get the PCB out? We can, basically, and we can unsolder the two wires that come from the switch. Yeah, the voltage selection. Basically, this switch is open when it's set to 240 volts, which is what I have. So we can just leave these wires open. We don't need to connect them together on our voltage supply. Probably easiest just to unsolder from the switch. Actually, let's get a bit of solder on that. Let's see if they'll just come off from here quite easily. Yeah, that one's off. This one. That one's off. Yeah. And then the thing can come out. Fan is holding it in place now. It's one of these cheapies, so of course they can't be bothered to actually fit a 2-pin plug down here. Yeah, they'd rather just solder the fan to the PCB. Are they labelled up plus and minus at least? Not exactly sure they are, but I can just put a little. That ends in minus, yeah. Again, let's see if we can just unsolder this. Yeah, that one's off. They're off, yeah. And now I think we've actually got the yeah, got rid of the casing. Okay. So there we have it. This is where we can connect our power, yeah. Let's have a good look at these capacitors, yeah. Yeah, okay, so this thing's got more domes than the skyline of Rome, yeah. More domes than the Basilica. Oh my god, okay, so before we do anything else, that's got to be sorted, yeah. I think the best thing to do is I'll just mark them with numbers and I'll take a photo so I know which one goes where, and then we can take them out and let's see what value these are. So let's see what we can actually replace them with, yeah. So just a marker pen, yeah. 1, 2, 3, yeah. 4, 5. This one doesn't look very good either. 6. This one's no good. 7 and 8. We have the other 3 actually look alright. I'm not saying they are, but they look alright. 9. Okay. So that's our motley parade of capacitors. Yeah. So I'll get these out and then let's have a look to see what we've got and what we can actually replace these with. Okay, so we've got a handful of capacitors here. Let's see what we've got. So we have some 1516, that one. 2210. What's this one? Another 2210. 1516. 1510. 1010. It's a bit of a mixture. 1510, 1010, and a couple little ones, yeah. So 470 16, and you know, there's another one. Yeah, a couple of 470 16s. Okay, let me have a look to see what we've got to replace these with. Okay, so I found some low ESR. These are 2216, so they can replace those two, yeah. That's replacements of those. Then I've got a few salvaged ones here. So we have 1516, yeah. I've got some 1516 here. Again, 105 degree. Let's have a quick look. Just I've got a couple of them. We'll just find a good one, yeah. Well, actually reads lower than you'd expect. Just try the other one. Oh, sorry, they're 1000s. They're not 1500s. Those are the 1000s. Yeah, these are the 1500s here. Yeah. So that's close enough. Yeah. And the other one, I only need one of these anyway. That also looks good. Yeah. Let's try the ESR meter as well. Just check these are low ESR. Yeah. So there we go. One ESR meter. Just connect our capacitor to this one and see what we have. That's really low, yeah. So that's a replacement for the 1516. I've got a couple of 1510. Again, I've got a whole bag of these, to be quite honest, that we can use. So let's just try a couple of these, see if these are any use. Yeah, so these ones again, they're 105 degree, yeah. Just check the ESR on these and the capacitance. So 1500 10s. Let's see what we got. Again, that's really low, yeah. So that's, as long as the capacitance is good. If the ESR is good, generally, really, the capacitance should also be good, yeah. So let's just check one of them. Yeah, fine. Capacitance on these should be 1500. What's going on with my capacitance meter today? I don't know why it's doing that. It's reading capacitors alright, but it seems to be like some interference going on or something it doesn't like. Yeah, plenty good enough. Yeah, 1500, over 1500. Plenty, yeah. So that's those. That just leaves us then with the 1000 10s, yeah. Again, I can find something. Yeah, I had these ones. Yeah, I've already measured the capacitance. So these are the 1010s. Quick check on the ESR on these. I mean, generally the lower the capacitor, the higher the ESR, but that's very good. Yeah. So that's replacement for those. Try another one. Yeah. So you can see, actually, you know, a decent ESR meter, it was like €40, but I mean, the money this is saving me just in, you know, salvage parts, yeah. The last two are the 470 10, yeah. So just check the 470 10 or 16. 470 16, yeah. Now I've got some 470 16s here. We've got the ESR meter to hand, so let's just use this. Yeah. It's a very low ESR, and on the last one, yeah. So we can be confident. I'll just check the capacitance of these two, but yeah, very good. So ESRs are all good, and just capacitance now on these 470s, yeah. I find generally salvage capacitors work very well. Yeah, plenty good enough. I mean, I do keep some, you know, the common ones. I do keep new. I buy 100 of them, yeah, motherboard capacitors and such like. But for this sort of repair work, I find that works fine. Okay, so let's replace all these nasty capacitors, and then let's see what this does. Yeah. Okay, so I've replaced all those capacitors. Yeah, I've got a nice colourful array of new capacitors here now. Yeah. So let's test this. These two wires went to the voltage selector switch, and when they open, that is basically set to 240 volts. So we don't need to worry about them. We'll get the light bulb. Let me just zoom out a little bit so you can see it. Okay, so I've got my light bulb letting me to hear the power's off at the moment. So we can plug the mains coming in here. I've got it connected to both bulbs, yeah, so I've got the 60 watt and the 100 watt there. Let's move this out of the way a little bit so nothing touches something it shouldn't, yeah. This thing's quite handy, by the way. It's called a safe block. Block spelled BLOC. I've had this since the 1980s. It's probably from the 70s. I honestly believe this wasn't new when I got it. It was not new when I got it. But these are great. They are like little clips here, so you can just connect your mains leads to it. And it's perfectly safe, even if this is plugged into the mains, because the mains contacts are up here basically. And it won't make a contact until you shut the lid, and now you can't touch anything. So yeah, if you can find one of them, they probably come under different names as well, yeah. So plug the safe block in there. That's all now connected up. We want our analyzer now, yeah. This is where you find out, by the way, if you put all the capacitors in the right way round, because if you didn't, something's going to go bang, yeah. To be honest, it'll make a fizzing noise first normally before it goes bang. So if you're alert enough and switch the power off quickly, it might not go bang, yeah. But yes, that's our analyzer. So set on the limiter, and we'll just power this up, yeah. Let's see what this actually does now. Well, it drew a little bit of power, and it's working, yeah. It's bleeping. Oh, no, it's not working. I have 5 volts low, yeah. I have 5 volts standby, but it says all the other voltages are low. Let's have a look with the voltmeter and let's see what we've actually got on the outputs, yeah. Let's see what we've got. One moment, I'll just get the meter. Let's see if that is actually correct, if all the voltages are actually low, yeah? I'll make a bit of space on the desk, one moment. Okay, well at least I've got the meter where you can see it, yeah? So let's power this up again. All voltages are saying low, yeah? Let's have a look what we've actually got. So this is 5 volts. Oops. Just connect my power lead in there, yeah? Oh, one moment, phone call coming in. Okay, so I mean basically 5 volts standby is now stable, yeah? We've got 5 volts. Oh, it's working. Amazing. No, it kind of came on for a moment. I saw all the voltages. Now it's going nuts and flashing on and off. Everything's gone unstable, completely unstable, yeah? Oh, it's back again. Can you see what it's doing? This thing's going nuts, yeah? Can you see it? It's like the power's pulsing on and off coming out of it, yeah? Let's have a look what we've got. Well, according to the meter, if we put it onto volts, yeah? According to the meter, yeah, it's going on and off. Can you see it? If I just, yeah, you see the whole thing powering on off, yeah. It's obviously not a happy bunny, is it? This one, yeah, not a happy bunny. So it's kind of like everything's pulsing on off now, yeah. But it seems to be somewhat intermittent. When I previously switched it on, it didn't quite do that, yeah. Let's just let it settle down a bit. Let's just try it again and see what it does, yeah. I'm on the light bulb limiter. Yeah, it's settled into this like everything pulses on and off, yeah. And then it kind of settles down a little bit and then starts doing it again, yeah. I don't know if you can see on the scale, you can see it, look how the voltages are coming and going, yeah. Let's try put a load on it. Let's switch off. Let's try putting a load on this, yeah. Let's have a look. So we can see that the brown wire in here on the orange, yeah. So it's obviously monitoring 3.3 volts here, yeah. And we need to connect a load to 3.3 volts. I'm going to use a 2 ohm resistor. I'm just going to unfreeze my camera, yeah. Okay, I've got this 2 ohm power resistor here, yeah. Connected a couple of crocodile clip leads. I've basically put the meter probes into the power supply on the 3.3 and on the ground, and connected the croc clip lead here as well, yeah. And if I switch my meter to resistance mode, I can see I've got about 2.8 ohms, so that's effectively the resistance of this and probably a little bit of resistance in the wires, yeah. So let's put it onto volts, yeah, and let's power it up again with a load on the 3.3, and let's see what it actually does now, yeah. Well, it's not very stable, is it? That's what it does now. It's obviously having some serious issues, this. I think the next thing is probably to change the capacitors that I didn't already change, yeah. I mean, some of them just looked okay, so I didn't actually bother to change them, yeah, because they weren't domed. But because of the way this is still behaving, I think we need now to test all those other capacitors as well, yeah. So we'll get onto that. Actually, let's have a look to see what's going on with this. We can always change these capacitors. The first thing I think we might check on this is whether or not the 5 volt standby is stable, because if that's going on and off or up and down, bearing in mind the 5 volt standby also repowering the pulse width modulator chip and the circuit that drives the main switching transistors. So if 5 volt standby is unstable, we can expect everything else to be unstable, yeah. Let's get some focus on that for you. There you go. So let's have a look at that. I'm just going to take these 2 wires off. These are the ones that went to the voltage selector switch, and we don't need them. if it's open, that's correct for our 240 volts. But they got high voltage on them, and I'm not too keen on them just like waggling around in the air. Yeah, it's just like, you know, you're just tempting fate. Yeah, so we can take these off for now. It's just keeps things a little bit safer for us. Just a bit of solder on that. And if you don't need to have wires hanging around with high voltage on them, then don't have them. Yeah. Okay, let's get rid of that one, and then the other one goes down between the two capacitors somewhere. Yeah, I think you see it. I mean, I could have always put a bit of insulation tape over the end, but I haven't got any insulation tape in the workshop. It's in the van. I tend to use that when I'm out on site. Yeah. Okay, so let's get rid of those. Just one hazard removed. Yeah, and now we can power it up. We don't want these things sticking up in the air. Yeah. So yeah, let's have a look. We'll put the analyzer back on, but let's have a look on the voltmeter, and let's try and determine what's going on the 5-volt standby. That's the purple wire, so I can see it comes up over here. Yeah, I'm sure it'll come from this diode actually. We've changed capacitors in this area. Yeah, let's have a look at that and see what we've got. I'll just connect it all. Right, we've got everything there where you can see. It's got the meter, it's on volts range there. The black meter lead is stuck into one of the grounds on the ATX connector. So I can now probe with this, yeah. So the first thing I'm interested to know is what's happening on this diode. This is your 5-volt standby. It looks like this has a chip here that generates the 5 volts, yeah. This diode I think will be the 5-volt standby, and probably this one down here, this one will be the other hidden voltage rail, the one that basically powers up this pulse width modulator chip over here, and the 2 transistors under here that drive this transformer, and via this transformer it drives the base of the switching transistors. Yeah, so this is the first place we're interested to see, is whether 5 volts is actually stable. Yeah, I'm going to switch this on connected via the light bulb. Yeah, so we via the light bulb limiter. So let's just power it up and see what happens now. Okay, well, if you see the analyzer, it's like flashing on and off. Yeah, like the power's going on and off. 5-volt standby does seem to be there though. Let's have a look. So on here, right, so the meter's also flashing on and off. Let me set it to manual voltage range. Yeah, just one moment. Right, that should be on the 20-volt range. Let's see what we've got now on here. It's going on and off. Yeah, you can see that. You can see that 5-volt standby is all over the place. Yeah, and let's try this little diode down here. I'm pretty sure this is the one that's generating the supply for the pulse width modulator. It might not be. I can actually see a negative voltage on that one. Yep, but we can say for certain that 5-volt standby is completely unstable. Yeah, and that's enough. We don't need to figure out what's on all the voltage rails. We need to fix that first. Yeah, without 5-volt standby, this is not gonna run. Yeah, we've changed the capacitors, most of the capacitors down here anyway. I'm interested to see where this pulse width modulator gets its power from. It must be coming from here somewhere. It may be this diode down here. So let's have a look to see what this chip is, and then figure out where that supply comes from. And then also let's have a look to see what this chip is, because I'm fairly confident, because it's right next to the transformer, this is what's driving, you know, effectively like a MOSFET is built in this chip. There's only 2 transistors on here. Yeah, normally you see 3, so one of them is driving the 5-volt standby. This has 2. So this chip, I'm sure, will be combined pulse width modulator and the you know, the MOSFET built in that to drive this. Okay, let's have a look anyway. I'll just trace through. So let's see what this chip is. Yeah. Okay, so these are the part numbers. This is an ST, that's the logo, SGS Thompson, I think this is 7502C. It says EST.7502C. I'm pretty sure this is the part number. The other one has a funny little logo on, an XY logo, then it says XY6112. So I'm thinking this is the one that actually is powering the transformer that's generating the 5-volt standby. This I think is this one here, yeah? I think is this. So let's have a look at the data sheet to see where this gets its power. But it's got to be coming from the 5-volt standby circuit somewhere, yeah? Okay, let's take a look. Oh, by the way, you've probably seen in the news we have a volcano erupted on Sunday a couple of days ago on La Palma, the island, yeah. And at the same time, I reached 1,000 subs on the channel, and people were commenting that some people have fireworks, but I went along and ordered the volcanic eruption, yeah. And I mentioned that we can't see it from here. I'll just actually show you on my desktop this photo I took myself, and I'm standing on the highest point on Gran Canaria here, yeah. So this is Pico de los Nieves, which is like the peak of the snow, basically, or peak of the snows, yeah. And this is the highest point, 2,000 meters high. And this, by the way, is Roque Nublo, Rock in the Clouds, which is the largest freestanding rock in the world, yeah. And this is Tenerife, Mount Tiri, which is the volcano on Tenerife. And La Palma is the other side of here, to be kind of like there somewhere, yeah. Somewhere in this area would be La Palma. And maybe if you stood up here, you could probably see the smoke coming up from that volcano if you drove up here and had a look. But anyway, if you have ever wondered what was on my desktop, oh, by the way, if you stand here and you look all the way round, you can see the ocean, the Atlantic Ocean. So from this point, roughly 12 miles in any direction, you will see the ocean. So you can stand here in the middle and you know you're on an island because you can see all the way around it, yeah? Okay, anyway, enough of that. But you know me, I like to waffle, yeah. So let's have a look to see if we can find these part numbers. So we have an ST, that's the maker, it's a 7502C, yeah. And it's we want the data sheet. Let's see what we can find. Oh, in fact, it's what there, EST7502C, that's what it's actually said on the chip, yeah. Yeah, I got you. Right, so let's have it. So this is the chip, yeah. All data sheet will find it. Well, actually, I've got what I need to know here. Oh, you know, this looks like a compatible chip. Is it with the 7500? No, that's a 7500. That's a TL494. No, it's slightly different. But we can see the power comes in on this pin, yeah. At 9, 10, 11, 12, 13, yeah. So we can actually have a look from pin 13 and see where that actually gets its power from, yeah. And this is a different pin out from the 494, it's not compatible, yeah. So pin 13 on that one. The other one was the XY6112 data sheet, yeah. Was this on all data sheets or somewhere? I tend to go to all data sheets if I can find that site, but anyway, it doesn't matter. Data sheet PDF. See if we can see this chip. Switching power supply controller, we kind of knew that anyway. And there's a bit about it, but not a data sheet. So you can just find the data sheet for this one. There's a picture of it. Oh, we've got a pin out at least, yeah. There's a PDF, let's have a look. And it's all in Chinese. But it kind of will tell us what we need to know, yeah. At least we got a pin out, and that's a good start, yeah. We've got a pin out. Okay, so I'll make a note of all that, then we can have a look on our board and see what we've got, yeah. Okay, I'm on resistance range now. So from the pulse width modulator chip, yeah, this is the one that drives the main switching transistors, right? This transformer and a couple of transistors down here, yeah. This actually, if you look via a 10 ohm resistor somewhere, which wouldn't be particularly strange. This actually goes to the 5V standby. Yeah, here. It doesn't go to this other diode. So this chip, from what I can see, is actually powered from the 5V standby directly. Yeah. Well, with a 10 ohm resistor in somewhere. In fact, I think I can see a 10 ohm resistor just here. Yeah, there's the resistor. So one end will go to this chip, I would think. No, maybe not. Maybe that was just chance. It was a. Let me just get onto the chip here. Let's have a look. No, not that 10 ohm resistor. But anyway, there is a 10 ohm resistor between here and here. Yeah. The other chip, the data sheet, as you saw, was in Chinese. Yeah, but this gives us a pin out for it. Yeah, so we can see what it does. We've also got a typical circuit diagram. Yeah. Now, the first thing we were interested in is VCC. Yeah, on this chip. That's the power to the chip there. Yeah, with reference to ground. Yeah. So we want to know what's on there and has it got a stable supply? Yeah, I suspected it probably hasn't, but there might be a good reason for that. So VCC is here, and we can see there's a capacitor, and there's a winding, a secondary winding on the transformer, the standby transformer. So this winding generates a voltage rectified by this diode, smoothed by this capacitor, and that's VCC. Now, you might wonder, well, that's fair enough, it's powered from here, but how does it power it when this transformer isn't running when you first switch on? This has got to start before it can generate its supply from here. Yeah, that's true. There's a resistor coming down here to this pin OB, and that might be, you'd think that might be a startup supply, so effectively when you first switch on, you get a bit of power down here. But if that was true, you'd have a capacitor here to ground. I honestly believe in the case of this chip that the high voltage from the switching transformer, the primary, actually supplies the initial voltage of the chip. Internally, if you like, there's a high value resistor from here to VCC. Yeah, and VCC has the capacitor on it. Yeah, so when you first switch on, I believe internally a high resistance powers here, yeah, charge the capacitor, that gets it going. This then starts to draw power, so the voltage here would drop. Yeah, and the way these are normally designed is this supply, this high resistance, can't keep this chip running. You can start it running, but once it starts to draw power, it starts to discharge this capacitor. Yeah, and basically the idea is before this discharging, this switch is off, this is supposed to take over this circuit, yeah, and keep it running. So normally when you first switch on, if you think about this, you get power, yeah. The high resistance starts to charge this capacitor, but it'll take, depending on the value of the resistor, it's probably could be like some mega ohms, yeah. That will take a few seconds. So it gives you effect like a soft start. So this starts to charge up, causes a little bit of a delay before this kicks in, yeah. And if this can't effectively run, it can't power itself, and it shuts back down again. So it kind of like self-protects, yeah. So what we're going to have to do now is have a look to see what is on pin 2 of this chip. Yeah, let's have a look to see what we've got there. Okay, to measure this voltage here, we have to measure to ground, but we can't measure to the ground on the secondary of this power supply because the primary is isolated from the secondary. This that it shows ground here is what is called hot ground. It's actually the negative end of the bridge rectifier, yeah. And depending on which phase, which half cycle of the waveform you're on, this point will either be connected to live or neutral, alternately, yeah. 50 times a second or 60 times a second in the US array, yeah. So we can find ground. The easiest point is this end of the bridge rectifier, yeah. If I show you on the board, you can see this is the chip, yeah. This is the capacitor that we can see. And if we go from the negative end of the bridge rectifier, which is down here, first of all, you'll find it's connected to this heat sink, yeah. So that's a good place to go ground. It's also connected to the end of this capacitor, yeah? But we actually know now that this is our ground, but it's also kind of live, yeah? It's not a safety ground. But that's where we can get our negative probe. The positive end, we can just go to the chip. Now, if you're the sort of person who's got shaky hands, yeah, and the more nervous you get, the more shaky they get, you want to be careful because you don't want to be slipping and shorting this to something else, yeah? The easiest way to do it is either solder a bit of wire on the board, and you even use a crocodile clip if you're worried about high voltages, yeah? Just have a crocodile clip and clip your meter probe on there. The other option you could do is actually just go to the top end of this capacitor, because that's fairly easy to get to there without shorting anything out, yeah? In this case, I'm just gonna probe the top end of this capacitor because I know I can go on there and not cause a short circuit, yeah? But for safety, just tack a wire on there with your soldering iron and just get a crocodile clip, yeah? I mean, at the end of the day, safety is paramount, so what you feel the safest to do, that's what you should do, yeah? I'm going to do it the way I've shown you, so, and that's because I believe that to be safe for myself. And the fact I'm quite experienced with working on this stuff, yeah? Okay, so we're on the volts range. So we're going to power the power supply up again. We're connecting it via the light bulb, so even if we do slip, it's not going to go bang, yeah? But it's not a good idea to be slipping with the emitter probes and this sort of thing, yeah? So let's power it up again, yeah? Lights on. The thing's flashing and bleeping away. Now let's have a look. So this is the ground, and we're going to go to the top end of this capacitor. And we can see straight away the power supply is coming and going there, yeah? I'll just put my meter onto manual voltage range. Let's go again. Okay. There you can see it. It's 5 volts, it's 7 volts, it's all over the place, yeah? Now, there's a couple of reasons why that could be happening here. We can assume, because it is running, that this startup supply has done its job and the power is now coming from this winding, yeah? But we know full well that this is switching on and off. So this switching on and off not only is going to cause the voltage here to fluctuate, it's going to cause the voltage here to fluctuate as well, yeah? And there could be a couple of reasons for this. But there can be several reasons. It has a feedback circuit here, yeah? So this opto isolator, depending on what's happening here, will affect the feedback, and the feedback will cause this to cycle up or down, increase or decrease the duty cycle, and effectively increase or decrease the drive, which will cause the output voltage to increase or decrease, yeah? And that output voltage down here is monitored by the LED in the opto isolator. So we have a feedback loop here, yeah? We have a feedback loop here. And I hope you can see that if something in this loop is unstable, it's all going to be unstable. Whether this LED is varying in brightness because it's a faulty LED, it's going dim and bright, whether or not the transistor here is conducting more or less, so it's a leaky transistor, whether or not this chip has got a fault, so it's not working properly, we have a feedback loop. Yeah? And the only way to diagnose what's going on here is to break the loop. Yeah, break the chain. And the way I'm going to do that, I'm going to trace through this LED, yeah? In fact, I might just find this end of this resistor here, yeah? And I'm going to disconnect this resistor, and I'm going to connect my bench power supply here. And I'm going to put in here a stable voltage, yeah? And by putting a stable voltage in here, in fact, I'm not actually going to do it from there. I just realised this is a TL431, yeah? This could also be unstable. This is the voltage reference, yeah? In fact, thinking about this now, the voltage reference should be stable. So the whole idea of a TL431 is that it should be stable, yeah? So this voltage here coming into this resistor, this jumps over, it's not connected here, that just goes past it, yeah? This voltage here should be stable in all cases, yeah, and that shouldn't be changed. Even though the voltage on here can be oscillating because this thing's going crazy, that should be the same. So let's check that first. Let's check the 431. If that is stable, Then we know the reference is stable, and then we'll do what we've said. We'll disconnect this resistor, we'll feed a stable voltage in here, and then see if it stabilizes. Yeah, if it then stabilizes, we know there's some problem in this feedback somewhere. If it doesn't stabilize, then we know there's something wrong with this. Yeah, that's the best way I can think to diagnose it. Okay, so let's find our chip here, and let's have a look. Yeah, to see what voltage we've got on the chip, the TL431. Actually, I made one slight error there. This point on the TL431 is connected to the bottom end of this opto-isolator, the diode, the LED. So basically, this effectively supplies a current to start this, but once current starts flowing through this resistor, this voltage will stabilise, yeah, and the voltage it will stabilise at will depend on the value of this one and this one, yeah. The voltage on this end of the LED will be stable. I'm saying about 2.5, but we'll find out in a minute, yeah. And the voltage on the other end of the LED will vary depending on the output voltage, yeah. Therefore, the brightness of the LED will vary, and that's what gives the feedback, yeah. Okay, so we can easily test this on the end of the opto-isolator, yeah. I've just turned the board upside down, you can see it here. I'm on resistance range, yeah, there you go. Resistance range, and this is our opto-isolator here, yeah. And that there is the TL431, these three pads, 1, 2, 3, yeah. So one end of this will go to the TL431. That end doesn't. Let's try this end. Yeah, this end goes to there, yeah. So the end of the opto-isolator nearest this edge of the board is the one we're interested in, okay? And we can have a look down here. Let's just get into view. So a bit different to the camera angle, but the opto-isolator is down there, yeah, between the two transformers. Can you see it? Yeah. And the point we're interested in is this end, the end nearest that end of the board, yeah. The voltage now, we're on the low voltage side, yeah. So now the ground for this area of the circuit, yeah, all this is on the secondary side, yeah. So in this case, ground now is a ground, like, you know, the black wires going to the ATX connector. So you always must be aware when you're working on power supplies where your ground is. The ground on the high voltage side is not the ground on the low voltage side. This side is safety ground, yeah. So I can stick my black meter probe straight down into one of the black wires on the ATX 20-way connector, yeah. Just find the get it in, it's in there, yeah. We're still in resistance mode, yeah. In fact, this is ground, yeah. This is ground as well. But we'll leave it where it is, and down here is our opto-isolator. So I'll stick my wire down here. We can go to volts. Yeah. And let's have a look now to see when I power this up. I just need to plug everything in first. When I power this up, yeah, what voltage we've got on this. This should be a stable voltage. I don't know exactly what it's going to be, but it shouldn't be varying, yeah. Okay, so I'm all ready to power it up. I've got my meter probe on the opto-isolator. I'm now on voltage range. We're still connecting via the light bulb, and let's just switch it all on, yeah? Oh, sorry. It didn't switch on my power switch. Now we're on. Let's go to manual range again. Right. It's all over the place. This looks like we've got sorry, I've lost one of the cameras, one moment. Okay, I'm sorry, I'm not quite sure at which point I actually lost the camera there. And save going back and checking the recording. I'll just do it again. So I'm on the end of the TL431 where it joins the opto-isolator, yeah. Power's on, camera's still working. And you can see the voltage there is not stable at all, yeah. It's all over the place. So the first thing looks like this is we've got some problem with the TL431. So let's take that off and we can actually test it out of circuit, yeah? Okay, here's the TL431 or equivalent, yeah? This one, you might just be able to make it out of the top line. It says AZ431, yeah? You get these chips made by lots of different companies, so you'll see different letters. You'll see KIA 431, for example. But it's a 431. It's a regulator, yeah. A programmable Zener diode rather, not a regulator. And the whole point of this is that it should have a stable voltage across the two outer pins, depending on the two resistors that feed the middle pin. Yeah, it should be stable. Okay, so let's have a look if this is good or not. I actually made a tester for these on the previous video, so let's get the tester and let's have a look, see what we've got. Okay, I've got a little tester here. I'll link to the video where I showed how to build this. It's basically just a resistor. Yeah, I've connected to my bench power supply. At the moment I've got 6 volts coming in, but the voltage isn't important. You could use a 9-volt battery, for instance. I'll show you that in a minute. So this is a KIA 431, yeah, and all we do is we hold it against these 3 pins here, and it should read 2.5. Yeah, 2.49. It doesn't matter which way round we put it. Yeah, 2.49. And again, it doesn't really matter what the voltage coming in is. If I turn the voltage up to 9 volts, yeah, it'll still be 2.5. Get contact against the board. Spread the pins out a little bit, yeah. Okay. There you go, 2.5, yeah. So let's try that now with our one that we've taken off the circuit board, yeah, see what this does. That's interesting, it's actually working, and I thought that would not be working. Okay, well, no worries. We'll put it back in. It actually is good. Yeah, definitely is good. And I'll just change the voltage supply there. Just put this back down to 6 volts, yeah, and you'll see that the voltage on this is the same, yeah. So we'll put us back in, and then we'll try the other thing I suggested, which is to break the feedback loop and use the bench power supply to power the opto isolator, yeah, LED, and then let's see what happens. I've changed the TL431 anyway. As soon as I had it out, I had a spare one. I thought I'll stick the spare one in, yeah, just in case something really strange is happening. But I was convinced that the voltage at the end of that should be stable, and I am still convinced, to be honest. The only reason the voltage at the top of the TL431 wouldn't be stable is if the voltage here drops below the reference voltage. So if say this was set to 2.5 and that goes below 2.5, then it couldn't be stable, yeah. So it may just be that, you know, effectively this is set to a different voltage, 3 or something. But what we can do is, I've just tried it with the other one, just you never know. If it still isn't working, I need to find out where all these resistors will connect together, yeah, effectively, and try and just put the 5 volts on here. I may just put 5 volts onto the 5 volts anyway on the 5 volt standby. You won't do any harm if I just stick 5 volts on the 5 volt standby, to be quite honest, to effectively force it to stabilize, yeah. The other option would be to maybe just to disconnect this inductor, but anyway, we can try. Let's see first if it is actually, by sort of bit of luck, actually working now, yeah. Okay, so let's try it and let's see if by any chance that's actually any more stable now than it was before, yeah. So let's have a look. This doesn't look like it. This is our 5 volt standby on the meter, yeah. And again, it's all over the place. Okay, so what we're going to have to do, I think, is to effectively drive this this part of the circuit, yeah. So I just need to trace it through now from the LED to have a look to see if I can find this resistor in this one. I'm sure our circuit will be very much an equivalent of this one, yeah. Let's have a look, just see if I can figure out where it's actually going. Actually, I didn't bother to trace it out because I'm being lazy today, yeah. So what I've done is I've taken my bench power supply and connected it to the purple wire, yeah, the 5 volt standby. And I've set the bench power supply to 5 volts. So you can see on the purple wire here now I have 5 volts, yeah. And this is the diode for 5 volt standby. I have 5 volts. So I've got a stable 5 volts there now. Now let's have a look to see what's happening on the photo transistor, yeah. So this is our end that's supposed to be a stable reference, yeah, 4.63. Another end is 5, yeah. So obviously the LED is turned off, yeah. There's only about 0.4 voltage difference, yeah. What happens if I increase the voltage on 5 volt standby? Yeah, you see there, it's suddenly triggered, yeah. Watch, bump, yeah. Just as I go up to 5.3 volts coming in, the end of the opto isolator now goes down to 1.9, yeah, and the other side is 3.8, so there's about 1.2 volts difference. So now the LED is turned on, yeah. And if I reduce the incoming voltage a little bit, just do it. There, it's turned off again, yeah. And the incoming voltage now is 4.9. So if I turn the voltage up just a bit above 5, the LED turns on. That's correct, because that's what it would normally happen. If once it reaches 5 volt, the LED turns on, yeah. So we now have a stable voltage on the LED. So what I'm going to do now is power this up with my 5 volt bench supply on the 5 volt standby. And I want to see if all the other voltages are now stable, yeah. So we get us ready to connect up. And again, we've got the light bulbs in, stop anything nasty happening, yeah. And we're just going to switch it on and see what we get, yeah. Yeah, so there you go. All the other voltage are actually reading low now, yeah. Let's see what we've actually got coming out of this. I'll go onto the, well, I'll do it on here. So red wires, naught. In fact, it's not running basically. It's not running now. It's only let's have a look on the actual chip. Yeah, that's the chip. So what I have now is I basically have no. Oh, maybe the earth lead wasn't connected. Let's just try again. Right, I have 12.4 on the 12 volts, yeah, that's stable. The ground wire wasn't connected properly. I have 3.3 on the orange, and I have 5 on the 5. So you can see if I stabilise the 5 volt standby, the whole thing stabilises. That's quite interesting because something in its natural state is not doing that. Let me have a quick think about that. Okay, just had to let my brain catch up with where I was for a moment there. So if we put 5 volts on the 5 volt standby, then all this is stable. And not only is it stable, but we can actually see effectively this thing working, yeah. If we increase the voltage here just a bit above 5, this LED turns on. And if we bring it down just below 5, it turns off. That is working, yeah. And with 5 volt standby, we've also got 5 volt supply to our main pulse width modulator, and the whole thing works, and all the voltages are stable. We can see them on the test meter, yeah. So what I think we need to do now is with the 5 volts on here, so this is stable, we want to have a look again on the VCC pin to our chip that's driving the standby. If this is not working properly, this voltage will still be all over the place because this is all over the place, yeah. So let's have a look to see if VCC is now still all over the place, yeah. If you remember, to measure this one, we have to go to this, which is hot ground, yeah, and we go to the top end of the capacitor here, yeah. So let's have a look. So again, we'll put our 5 volts power supply on first, yeah, and we'll just check to make sure from ground, find the ground to the LED here, yeah. So, sorry, to the diode here, yeah. And we have 5 volts, yeah. So from here now we're going to measure the VCC on the chip that's generating the standby. So let's switch everything back on. Okay, it is on. Now let's see what's happening on VCC here. Get onto it. And it's all over the place. Yeah. So we've now broken the loop, yeah. We've finally broken the chain and we can see what's happening. We know this part is okay, yeah. We know this is good now, yeah. We know that this is still all over the place. There's only one thing really left to check now, and that's this capacitor here, yeah. So we'll take this capacitor out because this is on VCC, yeah. We'll check this capacitor. If this capacitor is good, then I'm going to order a chip, yeah. While I'm at it, may as well just have a quick check of this resistor. But if that resistor exists, I mean, our circuit may not be exactly the same. But in particular, let's look at this capacitor, yeah. This is the capacitor. I also checked on our circuit, and the diode that feeds it, you can see on this application, the diode here, the other end of it goes directly to the transformer on this one, yeah. So that resistor isn't there. So we'll check this capacitor. Let's have a look to see if it's any good, yeah. That's the big question now. Is this capacitor any good? Yeah. Let's get the capacitance meter. What value is it? It's 47 microfarad, 50 volt. Yeah. So let's have a look to see if this is a good capacitor. Let's find the other meter lead. There we go. So it's reading a bit low. What's the ESO? Find out what that says. Sorry, you couldn't see it. I'm sorry about that, guys. I'll just do it again. So this is the capacitor. My capacitance meter doesn't seem to be working properly. I wonder if it needs new batteries in it, you know. I've got a capacitance meter on the fluke. So, sorry guys, I think that was my fault. Let's try again, yeah. Let's try again. I thought it was reading. Okay. Wrong meter leads. Too many meter leads on the desk, yeah. It's about 30. That's too low, yeah. Let's find that ESR meter now. Let's see what that thinks of it, yeah? ESR meter. Let's have a look. ESR's high. That's high. Let's try another capacitor. Let's find one. Okay, here's another one salvaged off something. It's 105 degrees C, same as the one that came out. Come on, we've got the SR meter first, so let's just check the SR on this one, and then we can check its capacitance. Yeah, so just stick the capacitor on here. Yeah, see the difference? Okay. Let's check the capacitance of this one. Okay. Very good connection on this. Dropped it. one of them days today, yeah. One of them days. Okay, let's see what we got. 49.50. Yeah, that's a good one. Okay, let's put this in here. Let's see what happens now. Yeah. Okay, so there's our replaced capacitor. Yeah. Let's just get some of these wires out of the way. I'm in a bit of a tangle here. Don't need the bench power supply anymore. Don't need the capacitance meters anymore. Don't need those capacitors. Let's make sure there's nothing under here. Yeah, that's going to cause any problems. That's fine. Okay. So once again, let's power this up and let's actually see what it does now. So this is going to be powered up without my bench power supply on the 5-volt standby. Yeah. I'll just set the camera so you can actually see everything. Okay, that's ready to go. Yeah, so let's see what it does now. And it's working. Yeah, I'll zoom the camera down. You'll be able to see all the voltages are stable now. Yeah, there you go. So yeah, one more power supply repaired. Okay, everything's fine there. Everything's fine. So in the end, it was in fact a capacitor. Yeah, I mean, we know all the ones in the output were bulged, they were bad. Yeah, this little one back here that was causing all the trouble. Think what you will of that repair. You could say that if I'd just pulled all the capacitors out and tested them or just changed them, I would have repaired it. And you're absolutely correct. Changing capacitors would have repaired this. And it may even say, and I think you'd be quite right, it was probably the quickest way to repair it as well. Yeah, but I think and I hope you'll agree with this, there is some value into the way we've tackled this repair. Not only was it a bad capacitor, but we basically proved where the problem was, and it came down to an IC or a capacitor. And I think we've learnt some interesting things from this video. So I think I hope you would agree that by doing it this way and proving where the fault is, in actual fact we've learned some skills and some useful hints and tips of how to tackle other repairs where we have an unstable circuit, which we had here. Yeah, okay guys, I'm sure some of you will be commenting in the section below, so yeah, let me know what you think, and I'll see you all soon on another repair video. Ciao for now, guys.